Well, this is Mr. Yeager. Today we're looking at velocity time and acceleration time graphs. So the last video was displacement time or position time graphs, and now we're moving on to basically the lower level, what comes from a displacement time graph. Obviously with the slope we can find the velocity. Basically we're going to solve the same things with a velocity time graph, but it obviously does tell us some different ideas. Okay, so here we go. So what is next? Okay, again, on a position time graph, that shows our displacement distance traveled. It tells us, the slope tells us the velocity, and then if there's a curve, it will show us an acceleration. Obviously, depending on the type of curve, it can either tell us that something's moving faster or slower. So again, what's next? The velocity time graphs. Okay, so if we look at this graph on the right, this was on the first page. All right, it's a velocity versus time. So I know you can already see kind of what it's telling you, but let's go through it slowly. So what does this show you? All right. So again, take this again just for what it is. Don't sit there and start trying to analyze it too much. All it's basically doing, what's it showing me, is it's showing me basically the velocity of the object at different times. All right. It's not showing me the distance that it is or where it is. It's just showing me, at close to 1 second, we're around 4.5 meters per second, or actually we're at 5 meters per second. All right. At 2 seconds, we're at 10 meters per second. Okay. So it's just telling me how fast the object is going. It's telling me the velocity of the object. Okay. The thing is, we can still do the same three things that we did with the position time graphs. You can tell me, is the velocity positive or negative or zero? Is the acceleration positive, negative, or zero? And then based on that, you can tell me, is it at rest? Is it at constant speed? Is it speeding up? Or is it slowing down? So we're going to do the exact same things, but we can't follow the exact same rules that we did with position and time. All right. So again, the difficult part of this is we now have two graphs, and the first step is, what type of graph do you have? Do you have the position time graph or do you have the velocity time graph? Because depending on which one you have, the slope means different things. What it's doing is different for both of them. So we have to be very, very careful. All right. So for a velocity time graph, the slope on a velocity time graph is the change in velocity over time. Again, slope is y over x. That's how we look at every single graph. All right. So what does that mean? The slope is the acceleration. Slope on a velocity time graph is acceleration. Slope on a position time graph is velocity. On a velocity time graph, slope is acceleration. All right? And so that's basically what we're trying to say. I keep on saying it over and over again. All right? So since the slope is acceleration, all right, I basically will look at that again. All right? So we know slope is acceleration. How do I then figure out if velocity is positive or negative or zero? All right? Because on a position time graph, I looked at the slope. If the slope is going up, positive. If it's going down, it's negative. So how do I figure out on a velocity time graph the velocity? Well, that actually a lot of students think all of a sudden it's easier. Know what it is? It's just where is it? Okay? Easy. The graph is telling you the velocity. Okay? Oops, let me go back real fast. All right, it's telling you the velocity. You can see by my picture. This is zero. Let me get my pen. Okay. This is a velocity time graph, so when you're at zero, that means you have zero velocity. I mean, that's one of the things that people don't see. Obviously, one mistake that people immediately go is they go, zero velocity is when you're at a flat line. That was on a position time graph, okay? On this now, each point is telling me a velocity. So the nice thing is, if I'm above zero, anything above zero is a positive velocity. When I'm below the x-axis, it's a negative velocity. So on this graph, it does depend on which side of the graph you are on. Above positive velocity, below negative velocity. All right? So that's how we can figure it out. Only when you're on the x-axis is your velocity zero. That is when you're at rest, is when you're on the x-axis. All right? So if we want to try to interpret this graph, Okay? The velocity. Well, which side is the line on? You're not worried about that the line's going down. That tells us something different. Okay? This is a velocity time graph. I'm above zero. So that tells me my velocity must be positive. I'm above zero. Okay? What about the acceleration? Well, the acceleration, that's the slope now. So that the slope of the line is downward. So that means that this must be a negative acceleration. Okay? So now if I have a positive velocity and a negative acceleration, what does that mean the object is doing? It must be slowing down. The other thing you should hopefully realize is it's telling you on the graph you're at 80 meters per second ending at 0. The only way to do that is if you slow down. So when the line approaches 0, the x-axis, you must be slowing down. When the line is leaving or getting farther away from 0, then you are speeding up. That's good for both sides of the graph. When you're below the graph, if you are below the graph, let's get the pen again. Okay? If you are below the graph, same thing. Same thing. If the line is going down, that is a negative acceleration. Does negative acceleration meaning you're slowing down? Hopefully we don't think so anymore. Okay? Negative acceleration does not mean slow down. All right? What's happening? You're getting farther away from the x-axis. All right? Remember, negative 10 meters per second is faster than negative 5 meters per second. All right? It's just faster in the negative direction. So be aware. That's kind of a little trick. If you get farther from the x-axis, you're speeding up. As you get closer, you're slowing down. Like this would be negative a, negative v. Over here, this would be negative v, positive a. You're slowing down for the line heading back toward the x-axis. All right? So hopefully you can pick some of those things out. All right? What's happening on this line? Well, here you go. So here's another example. You start at 0, basically is what I just talked about. It's going to be a negative velocity and negative acceleration because you're getting farther and farther and farther away from 0. Now, I know this one's a little confusing because you have your time axis there, but you can see you start at 0 meters per second and only get faster in the negative direction. Okay? All right. What about constant velocity? How can I have a constant velocity? Well, if the slope means acceleration on a velocity time graph, I have no acceleration when I have a flat line. It doesn't have to be down at 0. When I have a flat line, that means I'm still moving. I'm moving with a constant speed. Right here, what we're saying is at 2 seconds, you're at 10 meters per second. 3 seconds, 10 meters per second. 4 seconds, 10 meters per second. During that whole time, you're maintaining the same speed, always. Okay? So that's what we're looking at. All right, so we should see a flat line. All right. Only when you're on 0 are you at rest. Okay. So there's obviously the big things people make mistakes with the velocity time graph. I actually see more people do better with the velocity time graph, but we still make some mistakes. It's again, they look at a velocity time graph and they think and interpret it as a displacement time graph. Obviously, that'll be completely wrong. Okay, you have to while analyzing them similarly. What is V and A? You need to know how it depends on the type of graph. All right, so you got to be very careful. The nice thing is you shouldn't see curves on a velocity time graph. All right, if you do, all that means is that you have a changing acceleration. But we're not going to do many problems like that in this course. All right. There is one more thing that you can do with the velocity time graph that you cannot do with a position time graph. And that is you can find the area under the line. Okay? The area under the line actually represents the displacement. Okay? What's happening there is, let me go and grab my pen again. Sorry about this. All right, I haven't gotten into this yet. This is the first time we're seeing it, but this is another very important technique. Just like I said, and this is going to work for all graphs. Well, this is a technique we want to do for all graphs to see if it means anything. Like I said, when you see a graph in this course, and obviously we're starting with these right now, you usually want to figure out if the slope means something. How do you do that? You divide y divided by x. Whatever's on the y-axis divided by the x. That's why we see that this is change in velocity over time. The slope is acceleration on this graph. The other thing that you will do a lot, many times, is if the slope could mean something, but sometimes it doesn't. Maybe you'll get a graph where you do the slope and you go, that doesn't represent any formulas we've ever done. That might be fine. Then you might want to check the area. Area means you're going to multiply y times x. Okay, sorry, y times x. Okay? So we multiply. So let's think about this. Okay? If I multiply these two, velocity times time, well, that turns out that's the displacement. Okay? Because velocity is displacement over time. So if I multiply the time to the other side, all right, the area actually represents the displacement on this graph. Okay? So there's actually two pieces of information we could get from the velocity time graph. All right? The slope is the acceleration, area is the displacement. All right? Now the thing is, when you do area on a graph, again, you should probably already know this. Again, basically competent in algebra and basic graphing techniques. You basically change everything into a triangle and a rectangle. Don't try to, you can do trapezoids if you want. Okay? Trapezoids, the formula is 1/2 base 1 plus base 2 times h, if you want to write it that way. All right? You can do that. Most students change it into triangles and rectangles. So be careful. When I say area is y times x, there could be some factor like a 1/2 for triangles that we have to put in there as well. But it's still x times y or y times x. Okay? So we can find the area and that'll tell me the displacement. All it's telling me, the velocity time graph, it's telling me how far you have traveled. It does not say where you are. Okay, and I'll bring that back up probably on a later slide. All right, so what is the change in displacement on this graph? Okay, I would find the area of the triangle in the first section of the graph while the line is sloping up. So 1/2 times 4 times 8 is 16 meters. And I'd add that to the area of the rectangle, which is 48. So the total distance you traveled is 64 meters. Object has moved 64 meters. All right, but I want to make one thing very clear. Need that pen again. Okay. All you're getting with this is that you know that the object has changed its displacement by 64 meters. But I want to make this so clear. All right, a velocity time graph does not specifically say where the object is. All right. What we mean by that is be aware. Okay, this is one of those things that tricks people. A displacement time graph very clearly is telling you where the object is based on a reference point, based on 0. Okay. A velocity time graph does not tell you where you are. All right. It can tell you how far you've moved from some point, but it doesn't necessarily say, did you move 64 meters from 0? You have no idea. And some people go, well, it's 0 down here. Yeah, that's 0 velocity. That doesn't tell me that I'm starting at x equals 0. I could be at x equals 10. I could be at x equals -10. I could be at x equals 50. All right? So it only tells me how much I've changed where I am. So a lot of problems often go, you start at x equals 10. Based on this graph, where are you going to be after the 10 seconds? So when you find 64, that's usually a choice. That's usually an answer on like a multiple choice, but that's not the official answer. The 64 meters, you've moved 64 meters from 10 meters. So where are you now? 74 meters. Okay, and so forth. So be aware of that. It doesn't tell again, back up here. It doesn't tell you specifically where you are because it's only talking about the velocity. What you're going to see happen is as we basically go from displacement to velocity time, we're losing some information. We're getting more specific on certain things, but we're losing other information as we go down. Acceleration time. These are the the graphs that we get the least amount of information, and there's not a lot that we do with them. There's a couple of things we'll look at. For acceleration time graphs, it really will only tell you if the acceleration is positive or negative, depending on whether the line is above or below 0. So this is acceleration. All it's telling you is above the line positive, below the line negative. Okay? That is all you will need to know really with acceleration time graphs. Okay? For regular. For AP, this extra just to know is not extra just to know. You need to know this. For acceleration time graph, the area under the line is going to be the change in velocity. Okay, the area under an acceleration time graph is the change in velocity. I wish my pen would not go away all the time. Okay? All right. So that is important. Again, because if I do this area, all right, basically I'm doing acceleration times time, and that will equal change in velocity. Change in velocity divided by time equals acceleration. So they're the same formula. So when I multiply those, the area under the line is acceleration time. Most of these graphs are very simple. They're almost always flat lines, okay? Because we're going to do constant accelerations. We only want one acceleration for an extended period of time. So really with this, we're just above, below, or at 0 telling me about the acceleration, all right? The slope. The slope means nothing, okay? And that's because, this is an example of what I mean, where check the slope, but do we have anything that's acceleration divided by time? Do I know anything what a change in acceleration means over time? No. Okay? So we don't need to worry about the slope on an acceleration time graph. There's no term for it. We don't have anything. All it would mean is that the acceleration is changing, but there's no term for that. Okay? But usually that won't happen. We'll have a constant acceleration at different points in time. All right? As for converting graphs, okay, I guess I have this other video to look at. I'll probably go over that some a little bit later, okay? So the thing is, though, with it, I'll go and I guess talk about it some. When you convert graphs, make sure you understand that the axes always line up, okay? The object is moving, is changing displacement, is changing velocity, and accelerating all over the same time interval. So when I go from one graph to another, the time axes do remain the same. Okay? Again, the slope on a position time graph will tell you where to plot the velocity on a velocity time graph. All right? On a velocity time graph. All graphs must support the same type of motion over the same time frame. Again, you're going to get less and less information, but if you're telling me it's a positive acceleration on the displacement time graph, that better be a positive acceleration on the acceleration time graph. And I think I have some videos or animations here. Okay, so again, basically what we have here is you can see this object is moving at a constant speed to the right. Again, going back to dot motion diagrams, equal spacing. So it's moving at constant velocity, which means it has one velocity. On a position time graph, that would mean a straight slope. That would be a straight slope. On a velocity time graph, that would be a flat line. How do I know where to put this line? It's equal to this slope. So I could basically find the slope, and it, I guess, comes out to something like 11 or 12. It's going 12 meters per second. On a velocity time graph, it's a flat line. So what's the acceleration on a velocity time graph? It's the acceleration. If there's no slope, that means there's no acceleration. So it's a flat line. Okay? Leftward just means we're saying left is negative, so everything, a negative slope, a negative velocity, and zero acceleration still because it's constant speed. What if it speeds up? Okay, the dots are getting farther and farther apart. I get a curve. Now on this is where you're not necessarily going to calculate it, but you're going to have to pick out an appropriate graph that matches it. In this one, I have a positive velocity and a positive acceleration. So that's what I'm showing on the velocity time graph. I'm staying above 0, and it's accelerating positively, a positive slope. On an acceleration time graph, that would be a flat line in the positive section of the graph. How would I calculate technically the acceleration? It's the slope of the velocity time graph. One thing I want you to see is, as I go from position time to velocity time to acceleration time, I basically say the line is getting more simple. Okay? The line is getting more simple. What I mean by that is we're going from a curve to a straight slope to a flat line. Okay? When this was a straight line, when the position time graph was a straight line, velocity was a flat line, and then acceleration was at 0. So a curve creates a slope creates a flat line creates 0 on the next graph. Rightward velocity, but leftward acceleration, meaning the object is slowing down. On this one, I have a positive slope. It's still going up, still going positively, but it's a negative acceleration because we're slowing down. Positive v, negative a. That would mean on my velocity time graph, I stay in the positive range. I'm moving in a positive velocity, but it's a negative acceleration. And then on the acceleration time graph, it's a negative flat line. All right. I don't think I need to keep on going over these. I mean, just take a look at them. And again, try to see how we're changing from one type to the next type graph. All right. Again, I feel like the biggest mistakes are usually done on the velocity time, where people just go, wait a minute, the line's going up. Doesn't that mean it's getting faster? Okay? Or why is it in the negative range? That's just because it's a negative velocity, so just be careful. All right? So again, we're going to obviously go over this some, and AT will obviously move along a little bit faster, but we're going to have to interpret these motions, position time, find displacement and distance on position time, finding change in displacement on a velocity time with the area, being able to match up a displacement time with a corresponding velocity time graph. So it's not so much that you need to maybe make one compared to the other. We're going to practice that some, but there's going to be a lot more questions about, can you just be able to like interpret and go, this curve would create this appropriate velocity time graph? Can you do matching with them? Okay, and obviously be able to still interpret those dot motion diagrams. Okay, ignore this last thing. That's mainly for prior years. Okay, so that is it. All right, thank you.